Hello, I'm Alex E. Fenton Jr., a graduate student in the Brushwood Research Group at the Massachusetts Institute of Technology. Thank you for watching my talk. Today, I'll be discussing how electrochemical methods and probabilistic analysis can be used to infer failure modes in emerging energy storage technologies. I would like to begin my talk with a schematic that I'm sure many of you are familiar with. In the current energy grid infrastructure, large amounts of greenhouse gas emissions are generated, negatively impacting the environment. To alleviate this, renewable energy technologies are being implemented and indeed are becoming more cost effective. However, these technologies are plagued with intermittency. That is to say that the power generated by these renewable technologies does not always match the demand. To alleviate this intermittency, energy storage technologies must be developed and deployed, both immediately deployed to increase the viability of these renewable energy technologies and further iterated and developed to improve the capabilities of these energy storage technologies. Now, a wide variety of different architectures are being developed for grid-scale energy storage. Some examples include enclosed batteries, such as the lithium-ion battery, as well as open batteries. Take, for example, the redox flow batteries. Now, within each of these architectures, a large number of research avenues are being pursued. And a potentially non-obvious research avenue is the implementation of electroactive organic compounds capable of both donating and accepting electrons into both of these architectures. Now, the appeal for these electroactive organics comes in part from the fact that they are comprised of earth-abundant elements, but their major appeal comes from the fact that these organic compounds can be tuned to meet desired performance metrics through targeted functionalization of a parent backbone molecule. In the case of this molecule, targeted functionalization can improve the solubility, improve the stability, as well as tune the redox potential to a desired value. Now, this overall tunability makes organics very attractive, but a problem plagues them, that being that these organics typically decompose when they are cycled in a battery electrolyte. The way in which this occurs is that organics are originally isolated in a chemically stable form. Now, when this form is cycled in a battery electrolyte, an unstable form is accessed, which then decomposes into a variety of both electroactive and non-electroactive products. This limits the lifetime of these devices. Ideally, these electroactive organics would be stable on the order of decades. However, this is typically not the case, and it is important to note that this graph is not necessarily drawn to scale. Now, further targeted functionalization could improve the lifetime of these organics if the decomposition pathway is known, but more often than not, the decomposition pathway is originally not known. The approach to understanding the decomposition pathway is to identify the decay products. And then these products in turn can be used to backwork the pathway that led from the original organic compound to the observed products. This is typically done using a variety of ex situ techniques. And these techniques, one by one, eliminate compounds from the candidate set until a single compound or a set of compounds is identified as being present in the electrolyte. Now, this works, but the overall workflow has opportunities for improvement by incorporating electrochemical signals, which can be rapidly attained in electrochemical experiments and can often provide orthogonal information to that obtained from the chemical spectroscopic techniques. Take, for example, the electrochemical signals of a compound cycled here. The evolution of the electrochemical signal indicates that some transformation is taking place with the compound as it is being cycled in a battery electrolyte. So if this information could be quantitatively assessed in a fashion similar to that of these ex situ spectroscopic techniques, this overall workflow could be accelerated or further streamlined since data can be obtained more rapidly, and these electrochemical experiments may offer orthogonal information. Now, this is the goal that I'm pursuing, to incorporate electrochemical data into this analytical workflow. If we revisit these 4 compounds, and let's say that these 4 compounds are electrochemically active, each compound will have a characteristic signal. Now, information from this signal can be cataloged into a library, which in turn can be compared to experimental data. And through this comparison, certain compounds may be eliminated from contention. It is important to take a second here to note that all of this can be performed either experimentally in situ and with the help of computation. Following this, further chemical analysis can be performed to validate the findings conducted from the electrochemical analysis, as well as the identification of non-electroactive products. Now, while my vision is to develop this entire framework, for today, I will be discussing how a library, once it is already developed, can be compared to experimental data to eliminate compounds from contention. And I will do so using this example set of phenothiazines here, which are electroactive organics used as overcharge protectors in lithium-ion batteries, as well as high potential compounds in redox flow batteries. This particular set of phenothiazines were synthesized, purified, and sent to MIT from the Odom Research Group at the University of Kentucky. Now, the question I seek to answer with this study is, can the protocol that I have written identify a subset of these phenothiazines in an electrolyte? And this is done in 2 primary steps. The first is to identify the vector of best fit concentrations for each of these phenothiazines, whether the best fit concentration is 0 or greater than 0. This vector of best fit concentrations is then used to determine the probability that each phenothiazine is present in the electrolyte. So the vector of best fit concentrations is first found by referencing the library. In this particular case, if there are 2 compounds in the library, information from this library is used to simulate an electrochemical signal. In this particular case, a cyclic square wave voltammogram. Now we're interested in the concentration normalized difference current or concentration normalized electrochemical signal more generally. The reason being that this concentration normalized electrochemical signal is then compared to the experimental electrochemical signal using weighted least squares fitting, where we have the experimental measurement, the model response, as well as the experimental variance being considered to yield a vector of best fit concentrations, where the concentrations must be non-negative. And this vector is then output to the second major step of determining probabilities. Now, the question becomes, so how does this apply to this example set of phenothiazines? First off, the concentration normalized electrochemical signal, again, in this case, the concentration normalized difference current is simulated for each of these phenothiazines and shown in the graph here. Then this concentration normalized difference current is compared to the experimental data. Now, the experimentalist, myself, knew that these 2 phenothiazines, unsubstituted and methylphenothiazine, were added in solution beforehand. Now, these phenothiazines are fit to the experimental data to yield a best fit or a vector of best fit concentrations, as well as the best overall fit. So now the question becomes, how does this vector of best fit concentrations then help us determine the probability of each phenothiazine being in solution? This is conducted by asking a question. Is a particular compound X in solution? In this case, two models are compared using a metric known as the Bayesian Information Criterion, or the BIC for short. Here, n is the number of data points in the dataset, k is the number of adjustable parameters in the model, and L hat is the maximum of the likelihood function. Now, since rewards are negative and penalties are positive, better models have more negative BIC values, and these BIC values in turn are related to the model probability. So now, revisiting the two models, the two models considered is first, all compounds in the library are included, including the compound under consideration. The fit for this model has already been conducted. It's the vector of best fit concentrations. The second model is where all the compounds in the library except compound X is fitted. And so this fitting procedure must be conducted again to yield a vector of best fit concentrations, not including a compound of interest. And so the first model represents the notion that it is better to include compound X. The second says that it's better actually to not include compound X, that compound X is not in solution. The BIC is calculated for each of these values, and then Bayesian inference is performed using Bayes' rule to assign a probability of compound X being in solution. This is then repeated for compounds Y, Z, and so on. Now, in the case of the phenothiazines, when unsubstituted phenothiazine is excluded from contention, visually the fit is much worse. And this is reflected in a large difference between the BICs of the two models. Now, since the fit is much worse when phenothiazine is not included, we can say that phenothiazine must be in solution. And the case is similar with methylphenothiazine, even though the fit is visually better compared to that of unsubstituted phenothiazine. Now, with ethylphenothiazine, we see that the fit is just as good without ethylphenothiazine as when ethylphenothiazine is included. As a result of this, we can say that, no, we believe ethylphenothiazine is not in solution. And the case is the same for isopropyl and phenylphenothiazine. Now, these BIC values are then used to calculate what's known as the Bayes factor. And the Bayes factor is combined with knowledge of the prior probabilities to calculate the posterior probability. And when this calculation is performed for all phenothiazines, we see that unsubstituted and methylphenothiazine have probabilities of approximately 1, while those of the other phenothiazines have probabilities approximately 0, demonstrating that this protocol can correctly identify compounds. And so this is encouraging. This demonstrates that this protocol is capable of quantitatively assessing electrochemical data. So the next steps is to study more complex electrolytes. This can be done in part by integrating the electrochemical method just described with that of spectroscopic techniques, such as UV-Vis. And this combined can give the user greater confidence as well as help identify non-electroactive compounds in solution. More complex systems, such as those that have transient decay processes on the timescale of the electrochemical experiment, can also be performed. In this particular case, the decomposition of tert-butyl phenothiazine to that of unsubstituted phenothiazine. Further, these electrochemical probing methods can be used to monitor behavior in practical devices, and this has already begun. I would like to thank both my advisor as well as my research group for all the guidance they've given during this project. I would also like to thank the Odom Research Group for sending the phenothiazines, and as always, I am grateful for my funding. Thank you so much for your time and your attention. Hopefully, I've demonstrated how electrochemical methods and probabilistic analysis can enhance such an analytical workflow. I would be happy to discuss this further, and you can reach me at my email below.